There are some additional graphs that help you understand what it looks like. Here you can see the progression of chlorides over time. As you move this slider, the green indicates a higher level of chlorides. At year 62, this top of reinforcing the color at that, near that, should match up with the level necessary to initiate, which here would be the 0.15 for alternative 1. So it shows you how it's modeling the diffusion. It comes from the surface, works its way down uniformly across the concrete, and when it reaches the right level here, it initiates corrosion. Here are some additional graphs that show you what that progress is. So at the point of initiation of corrosion, this is what the two look like. So here's the 2-inch depth, the top of the reinforcing. At initiation, the base case has a percent weight of concrete of 0.05. Alternative 1 should have one that's 0.17. And these numbers don't match up because of variations in the way the graphs are made. So this is what the chloride levels look. As you move your way down into the concrete, you've got very high levels at the surface and they reduce down, and it's really at the surface of the reinforcing that matters most. Now on the right hand side, it shows you at the surface at that depth of 2 inches what the buildup rate is of chloride. So initially you have no chlorides on the steel, but over time this builds up fairly fast, and that's because the chlorides are moving faster, so you get higher levels sooner. By adding in the slag, silica fume, and nitrates, you're able to increase at a lower rate. This longer slope is really due to the slag, which affects M, and the silica and the higher level of concentrations are due to the calcium nitrite. And then finally, this shows you the diffusion coefficient over time. This is your best indicator of the ability of the concrete to withstand chlorides, because in the base case it's fairly high, which means that it can't withstand as well, so the chlorides move in fairly fast. These little wiggles are due to the annual temperature variations. The higher the temperature, the more diffuse it is. And here alternative 1 starts out at a lower diffusion and then moves its way and settles out at a much lower diffusion constant, which means it's more resistant as well. And then this shows you what the surface concentrations are over time, like I showed you before. If you had a barrier or sealant, then you would be lowering the amount of chlorides that are directly exposed to the concrete. Okay, so that's how you make your mixes. I'm going to go ahead and save to make sure we don't lose our work. Now, for the individual costs, there's three types that we're capturing. The first is the construction cost, what it costs to make the concrete itself. The second is any barrier costs or sealant costs you might have to apply to the concrete. And then thirdly, what the repair costs are. And following what was in version 1.0 or 1.1, you've got an initial concrete cost per cubic yard. If you want to modify these values, let's say alternative 1 costs more. I'm going to put in $100 simply because I want to change the value. This is the default. So now we've got two different costs per cubic yard. Other costs are used for this calculation as well. Here's the cost per cubic yard for the default. Here's the cost for black steel per pound. Here's the cost for epoxy coated. Here's the cost for stainless, membrane, sealants, and inhibitors. The reality is, in providing a methodology, is that over time these costs need to be updated. And really the best way to do that right now is for you as an analyst to look at those costs, and if they are very different than the costs that you experience in the field, to put what those costs are. So directly, if you see these for the first time, you can put in your own costs, and these as well, and then hit the Set as Defaults button. By pressing this, it will make sure that all future projects you have use those costs. For alternative 1, here are the different alternatives. For the base case, based on the particular mix that we've selected, we've got a 10,000 square feet at a cost of $3.63 a square foot, and there's the total cost for that concrete. Now, based on our repair costs over here, where we see the cost per square foot, the area that's repaired on average over the life of the structure, and our intervals, based on those, each cost is costing in today's dollars It's 1,000 square feet. It's only 10% of the overall surface. It's a cost is $37 per square foot, and that's the total cost in today's dollars of each repair. And then down here on the bottom, you can see a timeline of what those are. Here's the initial cost. After the red line, which represents the service life, you start the repair interval every 10 years. Compare that with alternative 1. When I do alternative 1, we have a much longer service life, and we're really down to a single or 2 repairs. That line right there really shows you what the benefits are of alternative 1. Let's go to life cycle costs. We have a whole series of graphs here that are meant to show you in as many ways that are useful what the relative life cycle costs are. So first and foremost, this diagram, or first it's showing you this table. Base case has a construction cost of $3.63 per square foot. Repair cost of $14, and that's summing up all the repairs over the life of the structure. So you've got 5 times as much repair cost as you do construction cost, and an overall life cycle cost of $18.42. Alternative 1 is slightly more expensive, but it has a much lower total summation of repair costs and gives you a much lower life cycle cost. And that shows you here in these graphs. This graph is meant to show you that comparison. And this is probably as good a time as any to say that if you wanted to grab this graph and put it into your own Word or PowerPoint document, you can copy it to the clipboard here and then paste it in. This graph shows you a comparison of the constituent costs that make up this life cycle cost. In terms of breaking down those life cycle costs over time, here is a series of graphs, and I'm going to go ahead, in the interest of time, show you all of the time series graphs together. Different ways of looking at the life cycle cost results. Here are the constituent costs over time. For the red is the alternative 1. Here's the construction cost per square foot, a repair for the base case, repair, 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 and a repair out here. Alternative 1, construction cost, only 1 repair. Over here, in terms of life cycle cost, you can see that this one starts out, cumulatively, it starts out with a higher life cycle cost, or construction cost, but over time it has much fewer repairs and takes an uptick in repair much farther out. So in the end, you can see there's a big difference in the summation of costs. Current costs simply tell you, they simply tell you what the inflated costs are going to be over time. So over time, things get more expensive, while today it's going to cost you, well, the first repair is going to cost you on the order of $4.80 per square foot. Those costs are going to go up over time due to inflation. And you see those here, and you see that here as well. These are sometimes called cash flow diagrams to give you an idea of the specific level of dollars you would spend. That's different than this, which actually discounts to the present value all of the costs. So you can look at that. You can look at it in terms of the structural dimension. You can look at it in terms of concrete volume, which would be by cubic yard of concrete, just to give you a baseline idea of what those costs are. And you can do it in terms of total costs. So in terms of standard reports, it will produce a report for you that shows you a summary of what your project is, the basic parameters of your structure, what your surface concentration level looks like externally, and what your temperature profiles look like. And these are important because they influence the external chloride and ultimately the service life. And then it gives you a summary of your mixtures. Base case has a WCM of 0.42, black steel. Alternative 1, we added slag and silica fume. We added an inhibitor. And then down here, it's showing you the diffusion properties and service lives. Life cycle cost report that gives you similar summary information. And that's shown here.